All right, now we're going to go through Unit 5.6. It's the 6th chapter in the 5th unit, and it's on historical and exponential depreciation. Now, in our last lesson, we went through linear depreciation, which basically meant that it went down a specific value every single year, but that value was the same. Here, with exponential decay or depreciation, we're looking at it going down a percentage rather than a specific dollar amount. Now we're going to have to do this a little differently because a lot of graphing goes into this, and I want to really emphasize how to get these particular values. So I've got the text up here, and we're just going to kind of review it for the first example, and then as we get into it, then we'll go back to the method that we normally use. So it says here, for example 1, determine an exponential depreciation equation that models the data in the table from the previous page. So in order to solve for this, it says here the exponential depreciation function can be determined by the exponential regression calculated by hand, by computer software, or a graphing calculator. You should have a TI 83 Plus, and if you do that, you will be able to go in here and follow this process. Now, it says when you use it on the graphing calculator, the data is entered into two lists as shown. And you can see that I've got it highlighted here on the right-hand side where it says L1, L2. And on list 1, it just lists 1, 2, 3, 4, 5. That's for each particular year. And L2 lists the value of the car for each year. It says the independent variable is the age of the car, and the dependent variable is the car's value. The exponential regression equation is displayed in the graphing calculator seen at the right. So when you go into your graphing calculator, you'll find an area where it says exponential regression. And it's y equals a times b to the x power, where x is your time in years. So let's keep reading. It says, notice that the general form of the exponential regression equation used by the calculator, it's slightly different than the one that was introduced when you were going through the vocabulary. So for ease of use, the numbers are rounded to the nearest hundredth, so we're only going to go 2 points after the decimal. So using the formula y equals a times b to the x, where a equals 25.921.87 and b equals 0.92. Now, how did I get that? I got that by the values that I listed up above into the calculator. When I went to the exponential regression, it went ahead and it gave me these numbers. And right below that, you can see where it actually graphs the specific points on the graph. The exponential regression is the line that comes through it here to show you where that exponential decay is happening. So the check your understanding says, how might a better fitting exponential depreciation equation look when it's superimposed? Well, you can see on this particular graph, and I'm sorry I can't highlight or actually even draw on this, but it won't allow me on a PowerPoint. You can see that the line is pretty close. It's a pretty good best line of fit, but there are certain ones where it literally goes all the way through, others where it kind of just goes up above it or down below it. So for it to be a better fitting, it just simply means that the graph would be closer to the actual data points. All right, let's go ahead and look at the second example. And it says, and I apologize here, what is the depreciation percentage for the 10 years of the car prices modeled in the exponential depreciation equation found in our first example? So it says here that we can recognize identify it by recognizing that B equals 1 minus R. So let's go ahead and go over to our example 2, and we said here that B equals 1 minus R, with R being my rate. So it says, determine what is the depreciation percentage over the 10 years. Well, I know that B equals 0.92. So if I plug that in, 0.92 equals 1 minus the rate. So if I move all of this stuff kind of over, if I'm going to add the r to both sides because I want the rate to be positive. So now I have the rate plus 0.92 equals 1. Remember, our goal is to get the rate by itself. So I'm going to subtract 0.92 from each side, and I get a rate of 0.08. Now that's as a decimal. Remember, if I want it as an actual percentage, I move it over, and the rate of exponential decay or regression is at 8%. Okay, moving on to example 3, it says Eamon purchased a 4-year-old car for $16,000, $16,400, and when it was new, it was sold at $23,000. So we've got to go back and remember the formula that we looked at in the beginning, and it was y equals a times 1 minus r to the x power. Let's break down what each of these are. A is my new car value. My r is my rate as a decimal. My x is time in years. So that's been pretty consistent throughout the whole course. Y is the car value at x years. So if it were, say, 3 years old, x would be 3, and y would be how much the car is worth at 3 years old. So what we're going to do here for the next quite a few examples is we're going to go through them and plug in what we have into our formula and solve for what we don't have. So in this particular case, we know that the new car value was $23,000. We know that the car was 4 years old at the time that it's asking us to rate it, and it was $16,400. So what we don't have here is the rate. So plugging in my values, I have $16,400 equals 23,000 times 1 minus r to the 4th power. So the first thing I'm going to do is go ahead and divide both sides by 23,000. And when I plug that into my calculator, let's go to the calculator real quick. So I've got 16,400 divided by the 23,000, and I get 0.713. So we get 0.713, here they cancel out, equals 1 minus r to the 4th. Now we've talked about before how to get rid of a square root. So what do we do when we've got it to a power with a variable inside? And the easiest way to do that is just the same way as we do when we're trying to break something down. So we're going to multiply this by 1/4 of a power. But again, remember, if I do something to one side, I have to do it to the other. So I'm going to multiply 0.713, and I'm going to do that to the 1/4 power. So let's see how good we are in doing that here on the calculator. So I get 0.713 to the open parenthesis 1 divided by 4 power. And I get 0.9189. Now it's asking us to go to the 10th of a percent, and I need to move it over twice, so I need to go out at least 3. So that's going to round to 0.919 equals, well, a 4 times 1/4, it does away with the power altogether. Now we're going to go ahead and add our r to both sides, and we get r plus 0.919 equals 1. We're going to subtract that 0.919 from both sides. And in the calculator, when we take 1 and subtract 0.919, we end up with 0.081 is the rate as a decimal. Moving over twice, I've got a rate of 8.1%. All right, please take a second to solve for this. When you're ready, come back. All right, let's see how you did here. When I plug in my values, I've got y is p, so it's p equals d times the 1 minus r all to the a power. So I know that I need to multiply both. I need to get rid, so I'm going to divide both sides by d. And that does away with that. So I have p over d equals 1 minus r to the a power. Next thing I'm going to do is multiply both sides by 1 over a. And my final answer, I end up with 1 minus p over d to the 1 over a. And there we go. All right, example 4. Let's go ahead again, A, R, X, Y. And it says it originally sold for $26,600. It depreciates exponentially at a rate of 5.5% per year. So as a decimal, that's 0.055. He puts $6,000 on the car and pays $400 a month to pay it off. After how many years will the car's value equal the amount he paid to date? So what we're going to have to do for this is we would have to plot and graph both of these. So we need to find our equations, and we will plot them. So the first one that we know is we've got y equals 26,600 times 1 minus 0.055 to the x power. So we're going to plug that into our graph. Next thing we need is our expense equation. So for that, we know that it was $6,000 down, that's our y-intercept, and $400 a month. So we've got y equals $400 per month plus the $6,000. Now there's one problem here, and that is this one is working in terms of years, whereas this one is working in terms of months. And we can't compare, again, apples to oranges. So what we're going to need to do is take that 400, multiply it by 12, so that we can get both of them in terms of a year. So my new equation ends up being y equals 4,800x plus 6,000. And if I put both of those into the graph, let's go ahead and go back to our textbook, and we're going to see what that looks like in our graph. So for example 4, you can see in the graph here that the point that you see this circle right here in where the pointer actually is, that is where the car is worth the same amount as what is owed on there. And if you can see that, it shows that if you scroll down here just a little bit, we're going to finish this example just right here. As we graph these, you can see here in this last paragraph down here, after approximately 3.3 years or 40 months, Richard will have paid about $22,000 towards the car, and he'll have a value of that same amount. Before that point, he owes more on the car than what it's worth. He's upside down on it. After that point, he has value on the car because he owes less than what is owed. And we'll continue in the second video.